Hello everyone, welcome to this video. I'll be talking about perceptron and multilayer perceptron, and I'll be implementing their models using the TensorFlow framework. So thank you, and let us begin. First of all, I import TensorFlow. Then I want to also import a file which will help me in visualization. So first of all, let us begin with the perceptron. The perceptron is one of the simplest artificial neural network architectures, which was invented in 1957 by Frank Rosenblatt. It is based on a slightly different artificial neural called a threshold logic unit, TLU, or sometimes a linear threshold unit, LTU. So when we see the architecture of a TLU, we see that a TLU accepts inputs and then it has the corresponding weights for the inputs, of which the weights and the inputs undergo a matrix multiplication, after which the matrix multiplication of the three inputs and the corresponding weights are summed and then passed through an activation function. In this case, the activation function is our step function. So let us go now to a perceptron. A perceptron is a linear binary classifier. It finds the most articulate boundary between two classes. So a perceptron is made of TLUs. So when we see the architecture for a perceptron, we see that it's made of TLUs in the output layer, of which the input layer receives the inputs and also has the bias. Then the output layer has the TLUs, which does the operations and then outputs the results after passing them through an activation function. So we see that the output layer does not have the bias neuron. Only the input layer has the bias neuron. And we will see that also in the multilayer perceptron. Only the input layer and the intermediary layers have the bias. The output layer has no bias. So therefore, let us look at the implementation of the model for a perceptron. So before we implement the model, we want to know what a model is. A model is a function that computes something on tensors, in bracket of word pass, and then in the process of computing something on the tensors, some variables can be updated in the response to training. So in this case, in response to training, the variables that are updated are the weights and the biases. Most models are made of layers. Layers are functions with a known mathematical structure that can be reused and have trainable variables. Of course, the trainable variables we know is the weights and the biases. So let us implement the model for perceptron. First of all, we define a class for perceptron. So tf.keras.model. Then we say we define an init function with the first argument being self, and then the in features to the perceptron. I set it to default to 1. Then the output features from the perceptron, I also set it to default to 1, and then I give the name as perceptron. So I go here, perceptron self, there. So therefore, after that, now I want to instantiate our weights and bias of the perceptron. So first of all, I start with instantiating the weights, tf.variable. So here I set random normal variables to the weights, with the shape being in features by out features. Then I set the name to be weights, and then I set it trainable to true so that it can be updated during model training. And then I go to instantiate our bias. So instantiate it using zeros. Then yes, the name becomes bias, and then I set trainable to true to enable the updating of the variable during model training. So after defining the init function, I define the call function where we'll have the operations of the perceptron occurring. So here we say y is tf.matrix. So here we define matrix multiplication of the inputs and the weights. Then I add to the bias. Then I return the bias here. So it's the output y that is taken to the activation function. In this case, it should be a step function and then returned. But now in this case, I want to forgo the step function for now. So these I've defined our perceptron. Now I want to train this perceptron model. So I'm going to use a dataset known as MNIST. MNIST is a dataset which is composed of images of values from 0 to 9, and then the outputs are the values, the numbers 0 to 9. So the MNIST was created so that you can use that dataset to train on images of the values and then predict the outputs as integers of 0 to 9. So I want to first of all call the it is inbuilt, it is found in the TensorFlow library. So here I say tf.keras.datasets.mnist.load data. So now we have our dataset, MNIST dataset, available to us. So if the dataset is in NumPy, so I want to convert the data to tensors. If you remember in the previous video, we used tf.convert to tensor extreme. So after converting to tensor, we let me define the data type of the tensor. So after converting it to a tensor, I want to also convert the labels, which are the integers for the images, the labels for the images. So I also say tf.convert to tensor y train. So before we continue further, the perceptron only accepts inputs as either scalars or vectors. It does not accept matrices. So since we know that our images are grayscale images and matrices, they are 28 by 28 in size. So since they are matrices, we can't use them as inputs to our perceptron model. We have to flatten the matrices to vectors before we pass them for our model during training. So hence I want to flatten the images. So I use tf.reshape. Then the first argument are the images, and then the second argument are the order of flattening. So yes, then after that I can also normalize the images so that there can be stability during model training. So then I run there, and so we have flattened our images and also normalized them in the range of 0 to 1. So if we see now our exchange shape, we see that there are now 60,000 images flattened to a vector of 784 elements. So we can also see that our labels are also 60,000 each, where each label represents the output of the image. So now that we have gotten our dataset and preprocessed it by converting it to tensors and flattening it, now let us create an object from our Perceptron class. So here our in features therefore will be 784, and then our out features will be since the labels are 0 to 9, so our out features are 10. So after doing that, then before we train our model now, we must first compile it. The reason for compiling is so that we can tell our model, basically the optimizer function that we are using. For now I can use the Adam, though you can also use RMS prop and others. And then our loss, I'll say tf.keras.losses.sparse category cross entropy. Then I pass an argument from logits equals to true. Then our matrix will be accuracy. So now I've compiled our model. So to train it now, I'll say perceptron.fit. The first argument is the features, in this case the images now flattened and normalized. Then second argument is the labels. Then I can also pass a third argument, the number of iterations that the model will pass through the data as it trains. I'll use 3 for now. Okay, 2. Then I'll also pass a fourth argument, validation split, where if the model is training, what percentage will it use for validation? What percentage of the data set? So if I say 0.2, it will use 20% of the data set for validation. So when we run it now, so here now we can see the performance of our Perceptron. We see that the loss reduced, which is good, and also the accuracy increased from 29% all the way to 75%, which is good. And we see that there is no overfitting, since the validation accuracy over here is more than the accuracy here, and also the validation accuracy over here is more than the accuracy here. So we see that our Perceptron can be trained further in order to learn the features and also give predictions based on the features that has learned. So now, since we've trained our Perceptron, we can now try to predict a value, a single value. So I want to import a single image from our test dataset. So I want to import a single image. So I want to take the first image. Here I'll say x test 0. So after importing the first image, what I do, let me pass a second argument constraining the data type to a float 32. So after passing in that image, I reshape it. From a matrix to a vector, since as we had said earlier, a perceptron does not work with input features of a matrix type. It only works with a vector and scalars. So we reshape it there, since it's a single image. So there, and then after reshaping, we do our normalization. So yeah, let me do normalization. There. Then since we cannot do prediction with a single image unless it is in a batch, we create a batch for the image where we say tf.expand dims, then we pass our image, and then we say 0. So in this case, the axis, the image will be batched on the outer axis, not really on the outer axis but on the first axis, since axis equals to 0. So now when we see the shape of our sample, we see that it's 1 by 784, meaning it's a vector image flattened to a vector of 74 elements inside a batch. So after flattening it, now we can do our predictions. So prediction is equals to do our predictions, we say perceptron, then x test sample. So now I want to wrap the perceptron inside the output of the perceptron inside an activation function known as softmax, which limits the elements to the range 0 to 1 and also limits the sum of the probabilities of the predictions to 1. So after I run it, now we get our prediction whose shape is a batch of 10 probabilities, of course, which the sum is 1. Now if I take the index of the maximum value of the probabilities of the predictions, we get that. So if I get the probability, I see that it's a 7. So let's see if our perceptron is correct. If the output of the first image of the test dataset is indeed a 7. So y test 0. So we see that it's a 7. So our perceptron is, as predicted correctly, the label of our image as a 7. So you can also use the matplotlib library to plot the image if it's 7 for further clarification. So that's all now on our perceptron. Now we are going to a multi-layer perceptron. So a multi-layer perceptron is composed of one input layer, one or more layers of threshold logic units called hidden layers, and one final layer of TLUs called the output layer. So for a multi-layer perceptron model, it must have at least one hidden layer for it to be called a multi-layer perceptron, of which the layers close to the input layer are usually called the lower layers, and the ones close to the outputs are usually called the upper layers. So every layer except the output layer includes a bias neuron and is fully connected to the next layer. So as we have seen, a multi-layer perceptron is just composed of many layers of a perceptron, as just says the name. So let us implement, first of all, we can see the architecture of a multi-layer perceptron. Yes, we see that it's composed of now in this case we have our input layer with the bias neuron of 1, our hidden layer with the bias neuron of 1, and our output layer, which we said does not have a bias neuron. So we can now implement our multi-layer perceptron. So I define our init function and say name is equals to MLP. Then I define this line. So now I can define the first layer to our perceptron. So layer 1. So in TensorFlow you can take a model and put it within another model. So in this case, to define our multi-layer perceptron model, we can define perceptron models within it and then relate them in terms of layers in order to get our multi-layer perceptron. So that's what I'm doing now. So say my sub-perceptron will have input features equals to 784 and output features. So I want the next hidden layer to get an input features of 16. So our output features here will be 16. So going on to layer 2, I will say perceptron. So in features will now be 16, and then out features I want it to be 8, and then now I'm going to define my output layer. Perceptron. So in features is equals to 8, out features is 10. So before I continue further, I want to say something here. This model that I'm creating right now does not accurately describe a multi-layer perceptron, since as we had said, the output layer for a multi-layer perceptron does not have the bias neuron. But since in this case I've defined the out layer using perceptron, which as we know, the perceptron model we created using also the bias layer, bias neuron, it will not accurately reflect it. So yes, that's the case. So I'm going to the call function. So within the call, I can say self.layer1, which will act on the input, Then the outputs will be passed through an activation function. In this case, I'm going to use the ReLU function, the rectified linear unit. Then the output, which is now our x, I'm going to pass it to the layer 2. And then the output, I'm going to pass it through an activation function. Again, I'm going to use the rectified linear unit. Then the output now, I'm going to pass it through our output layer. So I'm going to say self.outLayer of x. So in this case, our output layer, I have not defined the activation function for it. So after doing that, now this is our multi-layer perceptron. Yes, now this is our multi-layer perceptron. So we can now instantiate our multi-layer perceptron here. Now after instantiating it, I can compile it. As we had said earlier, we must compile it before we train it, so that we can tell our model the optimizer to use, the loss function to use, and the matrix to use. So in this case, it will be tf_keras.losses.sparse categorical cross entropy. Then I'm going to say from logits equals to true. Then matrix will be accuracy. Yes, so now let me compile my model. After compiling it, now I can train my model. I say x train or I train, and then I can tell it the number of iterations that we are going to take it through, and then the split of data set that we are going to use for validation. So there are very many more arguments that we can use here, but for now let us use these ones. So now I'm training my multi-layer perceptron. Yeah, so basically this is the outputs of a multi-layer perceptron. So you see that the accuracy increased and the loss decreased, which is good. So you can increase the number of epochs to train your multi-layer perceptron further and see the accuracy that it will achieve maybe after 20 epochs or more. So that is all on perceptron and multi-layer perceptron. So although for now we've created the models of the perceptron and multi-layer perceptron from scratch, the TensorFlow library gives us the options of defining them using functions within the TensorFlow. So we don't have to code the models from scratch. So the perceptron model, if I use the inbuilt functions of TensorFlow, I can say tf.keras.sequential, then I pass the input layer tf.keras.input, and we know that it accepts an input features with the shape of 784, and then it now has an output layer dense, and then the output is 10, since we are predicting values 0 to 9, which are 10 values. So in this case, the dense function is analogous to the perceptron which we had created earlier. So we have the input and the dense function. So in this case, now these are our perceptron model using inbuilt functions from TensorFlow. So we can then compile our perceptron model. So let me just copy from here to here. After compile, we can train our perceptron model. So epochs 2, then validation split 2. So what is the error? Expect x to be expect x to be a non-empty array or dataset. Okay, you can look at that and see what the problem is. So then also for the multilayer perceptron, we can say tf.keras.sequential. Then I can define our input layer. So our input will have shape of 784. Then I can say tf.keras.layers.dense. Then I can pass in an intermediary of, let's say now the output of this intermediate layer, I can say 16. Then I can say the output of this next layer is 32. Then now to the last layer, I can say is now our 10 for the 10 probabilistic outputs. So now, and then we can also pass an argument here known as activation. Now in this case, the outputs will pass through an activation function of the rectified linear unit. Here also, yeah. So now if we sorry about that, layers. So now I can compile my multilayer perceptron. So I say optimizer equals Adam, loss is equals to tf.keras.losses sparse categorical cross entropy from logits equals true. Then I say matrix equals accuracy. Then after compiling our multilayer perceptron, I can now train it. True validation split is equals to 0.2. So our multilayer perceptron is training. The first accuracy is good, 76. We can see the validation accuracy is also 92%, which is good. Then for the next second epoch, we see that the accuracy is 92%, the validation accuracy is 94%, which is also good. Yeah, so let us look back at the error that we received in the perceptron here, and we see what is the issue. So I've trained my perceptron model and I found it's now fine. So let us do our training. Train epochs is equals to 2, validation split equals to 0.2, perceptron. Nice, so it's working fine. Yeah, so it's working fine. So in this video we've seen how to implement the perceptron and the multi-layer perceptron models from scratch using the TensorFlow library, and we've also seen how we can use the inbuilt functions to define the mass perceptron and the multi-layer perceptron. So that is all in this video, and we can see that this way of defining our perceptron and our multi-layer perceptron, this is now the subclassed way of implementing models using TensorFlow. And when we go down here, this one is the sequential way. So this one is a sequential model, and the ones we implemented above are the subclassed models. So I guess that is all concerning the perceptron and the multi-layer perceptron and implementing the models using TensorFlow. So thank you so much for watching this video. I'll see you in the next video.